Right. Welcome everyone to today's seminar. Today's seminar will be given by Dr. Samuel Walton, who received his PhD in 2022 from Mullard Space Science Laboratory upon a part of University College London. There, he was investigating the statistical response of electron precipitation during geomagnetic storms, as well as in doing geomagnetic storm investigations of electrons using the Van Allen probes. Currently, Sam is a postdoc at the University of California, Berkeley, where he studies the dynamics of the coupled magnetosphere-ionosphere system, including the inner radiation belt, the outer radiation belt, and energetic particle precipitation. I'm happy to have Sam here with us today to discuss characterizing electron fluxes below the inner radiation belt. If you'd like to take it away, Sam.
Okay, thanks, Kyle. Thanks, everyone. Yeah, so as Kyle said, I'll be talking about energetic electrons below the inner radiation belt today. So I've been at UC Berkeley since January, and so I've been doing this work with Solène Lejeune and a little bit of input from Seth Claude Pierre and Leon Oliver as well. And essentially, what I'm going to talk about is how we've navigated actually isolating these kind of events and how we've put together almost a full statistical study at this point. And then a little bit at the end about the sort of future work that we're going to do. Here's the contents page. Yeah, so I'll start off with a radiation belt introduction, as might be customary in these seminars. And sort of the questions we're asking about this work, the data, and then take you through the work that I've been doing. So Earth's radiation belts. So we generally think of the Van Allen radiation belts as two separate bands of radiation around Earth, an outer radiation belt from about 2.5 to 7 Earth radii, full of trapped electrons of solar origin, and an inner radiation belt from about 1.2 to 2 Earth radii with electrons and protons of both solar origin and also cosmic origin. And here's a diagram here of generally the scale of the radiation belts compared to Earth. And they're made up of highly energetic charged particles, so from tens of keV, the ones that we look at anyway, tens of keV up to multiple MeV energies, which full of particles that gyrate around magnetic field lines and bounce between magnetic poles based on their pitch angle and the magnetic field strength. And so a full drift of an electron, for example, around the Earth would look like this simulation on the right here. And we're generally interested in the radiation belts because of their highly dynamic nature. So in both intensity and size and spatial extent, as you can see from this animation here, based on real data from a few days of SAMPEX measurements, I believe. And of course, that we all probably know that the justification is also from a sort of funding point of view and self-justification is that these can be damaging to our space infrastructure. So they can damage satellites, including some physical damage and damage to the electronics that we have on our satellites. This on the left is just an image from a lab test of a high energy electron fired at a solar array, which caused physical damage, which I always think is an interesting image to show. So that's our kind of justification. So the inner radiation belt that we'll be focusing on is, well, at least until fairly recently, before I started this work, I always sort of thought of the inner radiation belt as mainly protons and a process called CRAND, which stands for cosmic ray albedo neutron decay, which is essentially cosmic ray impacts the Earth's atmosphere. A decay process happens, which releases charged particles, then bounce off and become trapped in Earth's magnetic field. But what I hadn't heard too much of is that actually very deep injections of containing particles of solar origin are actually a big factor in the inner radiation belt's dynamics as well. So we talked about the inner radiation belt, but below the inner radiation belt is what we're going to focus on today. So how sort of looking at the dynamics of particles that go below around about an L shell, L shell in this case, of 1.2. And so if there's sort of a handful, not too many, but a handful of examples in the past of individual events being observed. So what we've got right here is a study from Richard Selesnik, 2019, that used the Demeter spacecraft to observe two events, event A on the top, event B in the middle there. And here we've got 215 keV electron volt electrons. And you can see event A there as Demeter passes through the sort of empty bit below the radiation belts and observes quite a strong enhancement there of 215 keV electrons. And then event B, there was two passes of the empty region. You can see on the contour, really small, but on the contours there, you can see L of 1.15, so very low L. And you can see sort of moderate intensity, 215 keV electrons there as well. And this association was made for each of these events, event A and then event B, both with typical geomagnetic activity. So you can see the DST profile here of a storm, and event A happened right in the recovery phase of that storm there. Also, actually, as DST starts to decrease again for maybe a second storm. I don't know what that has been classified as, but and then event B, not in the same places as event A during a storm, but in the just about in the recovery phase of a storm there, you can see the DST profile. And both of those events also associated with increased KP. So both observed during geomagnetic activity. And the closest thing to a statistical study I actually found was, well, a bunch of papers by this author who I've never met, called Suvarova. This particular one, Suvarova et al. 2017, who collected a bunch of below the inner belt enhancement events. So from now on, BIB is going to mean, when you see BIB, it means below inner belt. Below inner belt enhancement events at 30 keV. The first noticeable result from that paper was that the vast majority of those occurred during the declining phase of the solar cycle. And then the second one was associations were made strongly with various forms of geomagnetic activity. Or various measures of activity. So one of them being solar wind speed here, the distribution, normalized distribution of events, which seem to sort of have a tail distribution, but somewhat be associated with increased solar wind speed. And the same with the AL index there. So these kind of events, not too much work being done on them, but sort of somewhat being associated with geomagnetic activity, and a few observations of sort of maximum of 200-ish keV has been observed to get below the inner radiation belt. So the data that we've been using is Van Allen probe's data, specifically from RBSPB, because it seems as though that RBSPB's perigee goes a bit lower than RBSPA, and yeah, there was some inconsistencies with the energy ranges, so I decided to stick with RBSPB. And the data set we're using is a corrected a data set that's been put through a background correction algorithm that's described in Seth Claude-Pierre's 2015 paper, which essentially estimates the distribution of protons down at the low L regions, and then subtracts that from the measurements. There's lots of detail in the paper there, but it's quite interesting. And you can just see a few examples here of uncorrected data on the top row, corrected data in the middle, and the error on the bottom. And this is just electron flux as a function of time and L shell. And you can see that sort of the 100 keV here, most of the correction is coming in the slot region, the empty regions, and then as you get to the higher energies, lots and lots of proton contamination is being removed from this electron data at very low L. So that's going to be an important data set to use for low L shell observations, such as the ones I'm going to show you. So moving on to my analysis. So on the right here is an example of one of these particular events. And so what we've got is electron flux at various energies, as you can see the labels in the top right. So going from 30 keV up to 350 keV almost. Electron flux versus pitch angle and time. This is about 1 hour. And on the bottom panel there, you can see the L shell. That middle, that white dotted line is in the wrong place, but you could see the L shell dropping below L of 1.2, which would kind of, for now, I'll explain a bit more later, but for now going with as the lower boundary of the inner radiation belt. And these dotted lines are supposed to be when the spacecraft drops below L of 1.2, but I missed that. I missed that was wrong. And you can see the intense fluxes of the inner radiation belt. You drop below the inner belt, and in most of these energy channels, there's no fluxes whatsoever, no fluxes detected from tens of keV up to hundreds of keV, and then we go back above the inner radiation belt, and you see the intense fluxes again. So the obvious outlier here is in these two energy channels. So even though there's very few electrons at 31.9 keV, we get clear events that are going on, or clear intense fluxes that are being injected or transported below the inner radiation belt in these around about 40 and around about 75 keV energy channels, and then nothing again above that. And you might have also noticed that these dashed lines here, the sort of outer blue line being the bounce loss cone, the inner one being the drift loss cone, these are actually potentially could be getting lost to the atmosphere as well. So these are the kind of events we want to look at. And so the questions we're kind of asking for the rest of this seminar is how many of these events occurred during the RBSP era. So we have the whole 7-year Van Allen probes B data set with this background corrected measurements. And sort of how can we make any associations with these events and these events with geomagnetic indices and geomagnetic activity. And sort of we want to look at also the spatial profile of that and in relation to geomagnetic storms. So I've also done a superposed epoch analysis. But first kind of focusing on individual events, which I think are kind of interesting in themselves, just to sort of give people an idea of the nature of these observations. So here are two separate events again, and you can see the inner radiation belt, spacecraft drops below L of 1.2, all the electrons disappear, and then it goes back above 1.2, all the electrons reappear again. And the left event here is another example of similar to what we've seen before, where you get a lot of electrons that still persist at low L, but very low L, below L of 1.2, when the rest don't. There's virtually nothing there. And one of the more interesting events here on the right-hand side, so this is October 2017, at the lowest energies, there's actually not many electrons below the inner radiation belt, but then you go up to 130 keV, and there's a very clear presence of electrons there. And then there's a bit of a gap again at sort of a couple of hundred, and then we see electrons from 250 to about almost 346 keV below L of 1.2, so marginally below. You can see there from the L shell plot, marginally below, but that's kind of one thing that we genuinely didn't expect to observe, of electrons being sort of dead in some lower energies, nothing there, and then at higher energies seen very clear signs of either injection or transport or whatever it might be. So here we go. Yeah, another example. So this one goes up to 400 keV here. Even though there's not much going on at the lower energies, there's a clear sign of almost 400 keV electrons below the inner radiation belt, or below L of 1.2, because the definition can be subjective. So we decided to take all these events that we observed. So we used I think I might have had it on a slide already, but we used a algorithm that it's kind of a simple algorithm that we put together, which was just if we have a spacecraft pass below the inner radiation belt or below L of 1.2, and there's sufficient flux crossing that sort of gap while the spacecraft is below, then we count that as an event. Then we went through each one of them by eye to make sure that they weren't, I don't know, that it wasn't picking up something different, and the events were of this nature. So we plotted these passes, or sort of these perigees, where we saw events as a function of L shell and MLT, where the MLT of 12 hours is on top there, the sun will be on top. And you can see that there's a clear kind of distribution. There's a clear, it's not just random, sort of between 18 and 24 MLT is where the majority of our events were. And just by the way, just so you know, during this period, that the actual distribution of passes is pretty uniform. So it's not an artifact of the data. So you can see on the 18 to 24, you've got most events happening there. And then you've kind of got clusters of events in the morning sector as well, and just after noon. So not entirely sure what that is, but we also plotted the colors that you can see here. The lighter the color, the higher the maximum energy was that was measured by the spacecraft. However, the approach that we were taking here realized that there was a kind of flaw in that if there was a relationship between energy, which there probably is, between energy and how close to the Earth the electrons get injected, if the spacecraft goes too low, it won't observe that energy. So we realized there was a flaw in this kind of analysis. So which kind of leads me on to this plot, which is that the energy distribution of our events, just without any kind of MLT, which turned out to be really, really strange. So I still don't have an explanation for this. So according to this plot, there are loads and loads of events below 100 keV that sort of reach a maximum energy of no more than 100 keV. There's a huge dip between 1 and 200, and then another peak between 2 to 400, or well, 2 to 300, but it stays high above 300, and then tails off as you get higher and higher. So whether or not this is something I haven't thought of, which is like a bias in the data, I'm not sure. I really don't know, but it kind of puzzled me too much and was kind of getting me distracted from what I wanted to do, which was a statistical study. So we'll pick that up later, but we decided to take a different approach to analyzing the statistics of electrons below the inner radiation belt. So instead of events, we just wanted to decided to just look at the fluxes, the actual fluxes themselves, and do those statistics. So the problem here was, how do we actually define these fluxes, these electron fluxes that we're interested in? So we made a few of these distribution plots. So flux there on the x-axis and a distribution function, and this is for a particular MLT and L shell bin. And you can see here that for some reason, when Seth did his algorithm, wherever there was no flux measured, or it was below the noise floor, he set the value to 0. So basically, when we look at these distributions below the inner radiation belt, we removed all the zeros, and so the data that we're looking at is simply around about the top 1% of measurements below the inner radiation belt. So we chose an L of 1.2 as a sort of threshold. So when we're below L of 1.2, we only take the measured fluxes. So what for the rest of this talk, we'll only be looking at around about the top. This moves a bit depending on where you are, but around about the top 1 to 10% of measurements. So that was how we were going to isolate these interesting fluxes that to analyze in a statistical study. Okay, so the first thing, can we make a basic association with some forms of geomagnetic activity? So for now, we're sticking with the 59.6 keV electrons, the sort of tens of keV, just because there was a lot of data. We had to start somewhere. So we made association. We sort of plotted the median flux below L of 1.2 in our, of course, not forgetting, in our top 1 to 10% distribution, as a function of L shell and AE, solar wind speed, SIMH, dynamic pressure, and BZ. Also these values as a sort of maximum in the last 24 hours. So maximum AE in the past 24 hours, maximum solar wind speed, minimum SIMH, and so on. And the reason for that was because of the earlier studies that we saw with that Selesnik did, that there was a delay between any kind of event happening or at least some kind of delay between any kind of event and an event being observed, any kind of like storm, and then an injection being observed. Sorry. So the sort of three standout. So top here is median. The bottom is the 75th percentile, because we figured we were only interested in the more extreme events when we would get those injections. And there's three of these parameters are sort of the ones showing some kind of relationship. So AE in particular, maximum AE in the past 24 hours, you can see that as AE increases, you get higher fluxes below L of 1.2, and also there's a sort of relationship there where they're more likely to get to lower L as well. And the same with solar wind speed, and also the same with SIMH. So lower SIMH. We didn't go any lower than about I think it's about -60 or something, -70, because that's when the statistics break down and there's not enough data there. But clearly, as you get to lower SIMH, there's a higher chance of electrons being present below L of 1.2, and a higher chance that they'll get to lower L values. And then also dynamic pressure and VZ, not really much of a clear relationship there, especially compared to these other three. So we decided to focus on AE, which we'll come back to in a minute. But the second way we wanted to look at these fluxes was looking at the L versus MLT distribution of the actual fluxes, as opposed to the events that we looked at earlier, which again, kind of puzzlingly, is different to the distribution of events that I showed earlier with the peri-G passes. But what we've got here is for no particular geomagnetic activity. So no, what was I going to say? Yeah, nothing to do with AE or anything like that for now. Just simply the median on the left, upper quartile, and 90th percentile. Oh, sorry, that should say 95th percentile. 95th percentile of data on the right-hand side. Fluxes as a function of L and MLT, and this is all below L of 1.2. So just a quick description of what we're seeing here. There's not a huge amount of variation in MLT, really. That in terms of if you stick with one L shell, the difference is not huge. If anything, there's slightly higher fluxes on the dawn side of the magnetosphere. So between 0 and 12, maybe even between 18 round through midnight and round to noon. But there's not a drastic difference. And also the only other obvious thing is instead of fluxes between 0 and 6 tend to get to slightly lower L shell. You can see that in all three of these. But really, it seems to be kind of uniform, which I didn't expect as well. And as I said, these things won't have explanations yet, because I just wanted this to be an entirely sort of objective study of what we're seeing below the inner radiation belt. So that's one thing. We decided to look at this then, looking at the same plots, but with L versus ML, but with high AE values. So we've gone for, just to capture as much data as we could, we went for between 1 and 5,000 nanotesla AE. So the highest extreme of AE that we could look at and still have a good amount of data. And you can see, again, median up quartile, and then the most extreme data there, which again should be 95th percentile. Apologies for that. You can see just a more pronounced version of what we were seeing before. So this 0 to 6 MLT sector showing slightly deeper, slightly closer to Earth electrons. And then maybe slightly more MLT sort of asymmetry as well. So 0 to 6 to 12 to 18 showing the strongest fluxes, which is different to what we would see without any extreme AE activity. So it's kind of questioning a lot about this, about like, yeah, a lot of things happening here, which we really not sure about. We trust the data, but we're really not sure what's happening. So after this objective study, we'll certainly be going on to more like, how is this happening kind of study. So that's the sort of distribution, activity, and LMLT. So we've also done a superposed epoch analysis of these fluxes, which I thought was important to see things like the pitch angle distribution and how that evolves. It'll give us a bit of an idea of what might be happening to the electrons when they get there. So what we've got here is for 70 events identified using a DST storm list. And yeah, so sorry, the minimum DST was the epoch. So that's what this dashed line is here. And we're seeing again below L of 1.2, 50th percentile, so median electron fluxes at 60 keV as a function of epoch time and L shell. And as I've just said, the 0 epoch is minimum DST. And even with the median, so that not in the most extreme cases during storms, you can see that there's definitely a relationship between storms and these very low L electrons. So they tend to get lower as the storm progresses, or lower in L, and more intense right after the storm, and back again after. I don't know what this splodge is here to the left-hand side. I'm guessing that's a data-related artifact, but that wasn't clear on first look. And the pitch angle distribution is very anisotropic. So here's the fluxes again as a function of pitch angle instead of L shell. And this is for just all of the L shells from L of 1.2 to 1.1, just so it would collect enough data. And you can kind of see that enhancement there, but no obvious change in the pitch angle distribution. But when you look at, so same plot again, but the 75th percentile, things start to become even more clear. In the most extreme cases, you get, again, decrease in the L shell of these fluxes, followed by an enhancement, and then sort of going back the opposite direction as the storm progresses towards the end, 3 days after minimum DST. And then the pitch angle distribution starts to flatten a little bit, starts to isotropize a little bit after the storm, suggesting that when these electrons get below L of 1.2, they are actually being scattered somehow, or being lost to the atmosphere, which is still an open question. We don't really know what happens to them once they get there. And then 95th percentile, most extreme events, it has saturated the color bar there. So, but just to show the shape of what's going on, in the most extreme cases, again, dropping down to very low L, and then back up again. And then what we kind of reveal by going to the 95th percentile is the pitch angle distribution dynamics there. So as you get to the epoch of the storm, you can see that at the slightly lower than 90-degree pitch angles, you get higher fluxes. So again, could be a sign of pitch angle scattering of those electrons by some process. So yeah, at some point I would like to put the drift loss code on here, which I'm getting around to. But yeah, that's kind of an idea of the dynamics at very low L for 60 keV electrons. So the sort of final section is what was looking at the energy spectrum. So same superposed epoch analysis, but instead we've got these now again median fluxes between L of 1 and 1.2 as a function of energy and epoch time on the top. And then on the bottom there, we've got the profile, the energy profile, and the color represents the time during the storm. So the lighter the color, the later we are in the storm. And the energies go from 0 to about 1 MeV. Yeah, and we are still looking at 90-degree fluxes. So what we can see here that we sort of take away is that during the course of a storm, there's this kind of interesting cliff edge at about 2 to 300 keV. I think it's about 250 keV, where we tend to get electrons down below L of 1.2, and then this kind of aligns with other studies, but then above 250-ish keV, we get a drop off and there's no fluxes really at all. And you can see that in the profile here. Yeah, around about 250, it's a steeper, not quite a cliff edge, but a sort of steep drop off of electrons from 200 to 300 keV. But as we've done with the other plots, looking at this, the upper quartile, so the 75th percentile, this cliff edge sort of starts to become a little bit smoother, and you can see from the profile that it is less of a cliff edge. In the most extreme cases, it does seem that you can get higher energy electrons going below the inner radiation belt. And here during storms, this is during storms. So what you can also see there is that at these lower energies, you get increased intensity of electrons around minimum DST, which in this case seems to almost maintain its intensity as you go through this full 72 hours after minimum DST. But I think the main takeaway here is that this cliff edge that we thought was there, which aligns with other studies, here we're showing that during the most extreme times, that's not so much of a cliff edge. You can get higher energy electrons below the inner radiation belt. And then going up to the 95th percentile, just to drill home the point, it kind of almost disappears. It's just more of a smooth slope, where in the very most extreme of cases, you can get pretty high energy electrons going below L of 1.2. So almost finished. The kind of future work that we're kind of now looking at is we would like to do, so currently for our analysis, we've used L of 1.2 as our sort of cutoff. We've recently run for the entire Van Allen probes data set a calculation of the BLC, the bounce loss cone, and the drift loss cone. And what I want to kind of do next is tighten up that definition and say, well, the lower boundary of the inner radiation belt is less about a particular L value and more about actually where the drift loss cone is. And you can see here in this event that in the 74.9 keV, even though the drift loss cone is 90 degrees, in other words, every particle that goes down there should be lost to the atmosphere within a few hours, we're observing a strong signature of these electrons there. And the same goes for the other plots for the higher energies that I've been talking about. So whether we can do our statistics, if there's enough data, whether we can do our statistics based on whether particles are inside or outside the drift loss cone or the bounce loss cone, would give us an idea of what happens. And then a sort of speculative thing that me and Selene have been discussing is the fact that even though they're in the drift loss cone, they might not be lost, because this calculation isn't taking into account local electric fields down that low. And I think that's current global electric field models don't capture the smaller, more fine variations down at that lower L. So we, in the long term, want to sort of calculate an energy dependent drift loss cone, which factors in electric fields. And of course, the higher energies you get to, the less impacted by electric fields those particles are. So that could be an interesting thing to follow this up with. And I'm currently doing that now with the same statistics you've seen, but factoring in the drift loss cone and the bounce loss cone. And then going back to sort of the puzzling bit at the start, I would like to look at the list of events again and sort of probe more into what might be causing those weird energy distributions, because that was very unclear to me. And then especially looking at these higher energy events. So we showed an example of an almost 400 keV event where those energy electrons were getting to very low L below the inner radiation belt, which hasn't, as far as we can tell, as far as we found, hasn't been observed before. So typically we thought that it was only about a couple hundred keV that could get that low. And yeah, that's an example of that plot here. So the several hundred up to almost 400 keV will get in those significant injections below the inner radiation belt. And so quickly, just to final slide, going over what I've told you. We did a detailed analysis of 60 keV electrons below the inner radiation belt, and related those to different forms of geomagnetic activity. So we showed that relation to storms with the superposed epoch analysis, and then AE, solar wind speed, were the two, as well as, SIMH, which comes under the storms. AE, solar wind speed, and SIMH being the strongest looking relationships to what might affect these electrons below the inner radiation belt. Shown that there is a not drastic, but some kind of MLT dependence, especially, for the one we looked at in response to AE. And then the energy spectra is the sort of, I think, the most interesting thing here, where nominally there is a cutoff at 2 to 250 keV, but during extreme events, it might be commonplace for higher energy electrons to get below the inner radiation belt, which is, I think, where the bulk of the interesting work is here. So spare slides if questions are relevant, but thank you very much. And happy to take any questions.
Thank you, Sam, for a really cool talk. We do have a number of questions in the chat. Some of them are similar, or at least linked. So I'll try and group them together and combine a couple of them into one big question. So you did touch on this just finishing up, but Eric is wondering, can you postulate what might be causing the differences that you see in these events to occur at only one or a few energies?
So honestly, I really don't know, especially the higher energies. The closest I am with that is that, as I said, I kind of touched on, is that at that low of an L, we don't really have, to my knowledge, we don't really have that good of a understanding of the electric field dynamics down there. So we think that ultimately we'll get to that point of like pinning down that the electric field might be moving these electrons around. But in terms of the inconsistency of energies, I genuinely don't know what that might be. So I'm open to pointers in that regard.
Cool. So the next few questions are kind of about drivers and solar cycles, so I'll ask them together. So Hugh Hudson is wondering, how can the solar cycle influence these events, given that they're so far from the sun? And with a follow-up, we have David Pitchford, is there any correlation of these with high-speed solar wind streams? And then finally, Jason Durr, did you check whether there's any interesting correlations with BZ being greater than 0?
So I'll kind of try and go back to the first part of that. So how can the solar cycle possibly influence these events so far from the sun? So I guess when you get big events like geomagnetic storms, that influences the entire magnetosphere. So which can go further, the plasmasphere moves to very low L. And my knowledge is kind of limited here in all the very detailed stuff, because I am still learning about all these detailed processes that go on at low L. But as I understand it, the sun activity on the sun can influence the entire magnetosphere. So I don't know if there was a more like specific.
Yes. So I meant to ask that as a more leading question, which I sort of grouped together better. So Jerry's wondering if it could be high-speed solar wind streams, and Jason's question I think might come towards CMEs as well, and CIRs and different BZ profiles. So I was wondering if it's possible that different solar wind drivers might be driving some of this activity.
Okay, definitely possible. So not something we've looked at yet. I guess that's like something separate superposed epoch analysis, but with separating for different storm drivers. Certainly something we'd look at, but yeah. But the short answer is don't know yet.
So Joachim has a similar question, but this time regarding substorms. Have you looked beyond AE, and did you see any other relations with substorms and injections at these low L values?
Yes. So we have looked beyond AE. So we mentioned that there was solar wind speed was also relevant. So actually it might tie into the previous bit, but we looked at all those parameters we showed before. So it was like right at the start somewhere. I'll not get the slide up, but we looked at solar wind speed, dynamic pressure, all those kind of things. And then in L versus MLT in the energy spectrum, we looked at solar wind speed and SIMH as well, and they all showed kind of similar things. So that's why I only showed AE, because it gave us the clearest plots, but all showed similar relationships. And then the solar kind of just coming up into my head right now, but the solar wind speed could be related to the different storm drivers. So that might be something to look into in more detail. But there was one, so substorms was another part of the question. We did a superposed epoch analysis with substorms, but I haven't shown it or talked about it yet because I'm not convinced that the data is good enough. But I need to check that again. I kind of left it because I wanted to progress this, but as we start to tie this up, I might go back to substorms. But it did show a really clear relationship, but again, I wasn't convinced with the data, and I was kind of battling with, well, what actually is a good way to do a superposed epoch analysis with substorms, because I'm not a substorm person, but from when I talk to someone, whenever I talk to anyone, they tell me there's lots of different definitions of how you can do that with substorms. So short answer is yes, we have looked more into substorms, but I kind of haven't nailed it down yet.
Okay, cool. And then there's a final question, again by Jason Durr. Do we get many injections into the mid to low latitude ionosphere from these Bib particle losses?
So the mid to low latitude ionosphere. So yeah, I should have added these plots in, but I've recently done like a geographical map of these fluxes, and in the statistics anyway, they didn't seem to be a huge amount of, so it didn't show much of a relationship when we plotted these statistics on geographical maps, other than just the radiation belts becoming more or less intense. So at this point, I can't see much in the way of like some kind of geographical relationship. However, the Selesnik plot that I showed earlier, I will actually bring it back up. There we go. Show that, very low latitudes. They've observed these 200 keV events. So whether when we look closer at the drift loss cone, bounce loss cone stuff, we'll see more of a geographical relationship. But as of now, we haven't.
Okay. So just as a follow-up to that, have you looked at whether there are any good alphane or opposed conjunctions? The overlap with alphane is very small, but that might give some intuition as to the precipitation into lower latitudes here.
Say that again. Sorry, I was distracted by another message popping up.
Have you investigated whether or not there are any conjunctions with alphane? CubeSat for some of these Bib events.
Elfin. Oh, no, we haven't actually. That might be something to do.
That might be a way to address Jason's question and to see if there's anything peculiar happening in the ionosphere as well.
Yeah. And the message, I just want to follow, the message I got distracted by was Jason saying it wasn't much about geographic relationship, but whether the particles are getting lost to the ionosphere. So that is a question we're actively trying to answer. So even though in our plots we can see some of these electrons are in the drift loss cone, we're not 100% sure at that low of an L whether they are actually being lost or not. So that's like the ultimate question here, if you like. So when we do incorporate these electric fields somehow, that might answer that a bit more. Hopefully that's answered your question a bit more.
Excellent. Well, thank you very much, Sam. This was a really cool talk. Our next talk will be next Monday. Oleksiy Agapitov will be discussing coarse and Higgs spatial scales in the inner magnetosphere. So thank you again, Sam, and I hope you have a wonderful morning. I hope everyone else enjoys the rest of their week.
Yeah, thanks, Kyle. Thanks, everybody.